So our discussion is on thin-walled pressure vessel. So a tank or pipe carrying a fluid or gas under a pressure is subjected to tensile forces which resist bursting developed across longitudinal and transverse section. So for this illustration, we have a figure. You have a tank that is carrying a gas or fluid that is under pressure denoted by P, and that is subjected to tensile forces denoted by T and a bursting force denoted by F. So if we try to isolate the right half of the tank, so you now have the figure. So if you're going to observe on the right half of the tank, we have the tensile forces denoted by T, which resist our bursting force. Our bursting force denoted by F. So our bursting force F is equal to pressure times the area. And the area is equivalent actually to the diameter of the tank multiplied to the length of the tank. And our tensile forces is equal to tensile stress multiplied to area of the wall. And the area of the wall is equivalent to the thickness of the tank and the thickness of the wall of the tank and multiplied to the length of the tank. So therefore, based on our illustration, if we're going to have the summation of forces equal to 0, we can have F is equal to 2 times T. If we try to substitute the value for F, which is pressure P times D times L equal to, our T is equal to stress multiplied to our thickness of the wall of the tank times the length of the tank. So if we try to simplify this one, we can get the value for the stress, which is the tangential stress, is equal to pressure times the diameter all over 2 times the thickness. So if there is an existing external pressure piece of O and an internal pressure piece of I, the formula may be expressed as you have tangential stress is equal to piece of I minus piece of O times D all over 2T. Okay, let's have now the longitudinal stress. So we try to consider the free body diagram in the transverse section of the tank. So if you're going to observe here, you have a force that is acting on the rear tank portion of the tank. So that is denoted by capital letter F, and it should be equal to the total longitudinal stress on the wall, which is denoted by piece of T. And piece of T is equal to stress multiplied to the area of the wall. Since it is so small compared to the diameter, since the thickness is very small compared to the diameter of the tank, the area of the wall is close to pi diameter times the thickness. So based on this illustration, so our F here is the equivalent to pressure times area, or that will be equivalent to pressure times d squared all over 4. And our longitudinal stress, piece of T, is equal to stress on the wall times pi times D times T. So therefore, if we try to have summation of forces horizontal is equal to 0, we can have piece of T is equal to F. If we try to substitute the value for piece of T, which is longitudinal stress times pi times D times T, is equal to stress times equal to pressure times pi all over 4 T squared. So therefore, our longitudinal stress is equivalent to pressure times the diameter all over 4T. So if there exists an external pressure piece of O and an internal pressure piece of I, the formula may be expressed as longitudinal stress is equal to piece of I minus piece of O times D all over 4T. it can be observed that the longitudinal stress is twice that of the longitudinal stress. So therefore you have tangential stress is equal to 2 times longitudinal stress. For a spherical shell, if a spherical tank of diameter d and thickness t contains gas under a pressure of P, the stress at the wall can be expressed as longitudinal stress is equal to P sub I minus P sub O times the diameter all over 4T. Okay, problem number 1. A cylindrical steel pressure vessel 400 mm in diameter with a wall thickness of 20 mm is subjected to an internal pressure of 4.5 meganewton per meter squared. Letter A, calculate the tangential and longitudinal stresses in the steel. Letter B, to what value may the internal pressure be increased if the stress in the steel is limited to 120 meganewton per meter squared. And letter C, if the internal pressure were increased until the vessel burst, sketch the type of fracture that would occur. So for this one, for our letter A, the tangential stress on the longitudinal section, we will have the equation. For our letter A, we have our equation which is F is equal to 2T. So, of course, our F is pressure times diameter times the length of the tank. This is 2 times our T, which is stress, tensile stress, multiplied to the thickness of the wall of the tank, multiplied to the length of the tank. So, tangential tensile stress equal to, or the tangential stress rather, is equal to PD all over 2T. And if we try to substitute the value, our pressure is 4.5 meganewton per meter squared multiplied to the diameter, which is 400 mm all over 2 times the thickness, which is 20. So therefore, our tangential stress is equal to 45 megapascal. And for the longitudinal stress, which is on the transverse section, longitudinal stress so we have here F is equal to P. So the total force acting on the rear portion of the tank is equal to our total longitudinal stress on the wall denoted by P sub T. And of course, if we try to substitute the value for F, which is 1/4 times pi d squared times the internal pressure is equal to the longitudinal stress is equal to stress multiplied to pi times the diameter times the thickness. So therefore, our longitudinal stress is equal to PD all over 40. If we try to substitute the given values, we have 4.5 times 400 all over 4 times 20. So therefore, our longitudinal stress is equal to 22.5 megapascal. For letter B, the internal pressure may be increased if the stress in the steel is limited to 120 meganewton per meter squared. So from our illustration, we have identified that our tangential stress equal to P d all over 2T. Internal pressure times the diameter over 2T, and our longitudinal stress equal to internal pressure times diameter all over for T. So we have the conclusion that our tangential stress equal to 2 times the longitudinal stress. And this shows that the tangential stress is the critical. So therefore, since the tangential stress is critical, so we try to compute for our P based on the tangential stress formula. So we have here from this equation, so we have 120 is equal to internal stress or internal pressure times 400, which is diameter, or over 2 times our thickness, which is 20. So therefore, our internal pressure is equal to 12 megapascal. For letter C, the internal pressure will increase until the vessel bursts. Sketch the type of fracture that will occur. So this is our letter C. So the bursting force will cause a stress on the longitudinal section that is twice to that of the transverse section. So therefore, the fracture is expected as shown in the figure. So we have here the illustration. We have the expected fracture when internal pressure is increased until the vessel will burst. So this will be the illustration. This is where the internal fracture will occur. Problem number 2. A water tank 22 feet in diameter is made from steel plates that are 1/2 inch thick. Find the maximum height to which the tank may be filled if the circumferential stress is limited to 6,000 psi. The specific weight of water is 62.4 pounds per cubic feet. So for this a problem, we have now the illustration. So of course you have the bursting force F, and we have your tensile forces, the resisting force, which is denoted by T. So we are given with the diameter of the tank 22 feet. And we have to convert first our stress, our circumferential stress, since this is PSI. You can convert this one to pounds per square feet. So therefore, if we try to convert, we have 6,000 pounds per square feet times 12 inches all over feet raised to the second. So it gives us 864,000 pounds per square feet. So we try to assume that the pressure distribution is uniform. So of course, we have our equation F from summation of forces equal to 0. So we have F is equal to 2T, where our F is equal to our internal pressure times the area. So our pressure is actually equivalent to gamma times H, and this is actually equivalent to 62.4 of H. So therefore, our F here is equal to 62.4 H times our D times our H. And it gives us now F is equal to 62.4 times 22, which is our diameter, then multiplied to our H squared. So therefore, simplifying this one, we have 1,372.8 H squared. And our T is equal to stress times the area, and we have now our stress, which is 864,000 times T, the thickness times the H, and this is 864,000. Our thickness is 12 inches. Convert this one to feet. So 1/2 times 1/2 inch times 1/12 conversion to feet times H. So we get the value for T, which is 36,000 of H. So therefore, from our equation, F is equal to 2T. So we simply have to substitute to 1,372 0.8 h squared is equal to 2 times 36,000